Hello, how is it going? Let's see. Oops. Sorry for the glitch. Welcome back. It's been only a week, or maybe even less. Was it last Thursday, last Wednesday? We had our previous tech talk. We're back. It's pretty nice actually to be able to have that many episodes as of late. Today we're going to talk about all things video and video and image processing. It's an area basically in Zephyr that's pretty active these days, and we will have one of the maintainers of the video subsystem talking about not only video in Zephyr, but actually there's also some like really cool developments in the form of external libraries and modules that you can use with Zephyr or possibly with other embedded platforms to do really like interesting image processing on really tiny MCUs, which is what you're here for, right? Basically, I think by now, people joining the stream, one way or the other, you're interested in hopefully and ideally in Zephyr, but just probably in all things embedded in microcontrollers in general. I'm Benjamin. I'm your host for today. I'm joining from France. How about you folks? Tell us whether you're joining us from YouTube, from LinkedIn. Drop a comment in the chat. Say hi. This is our sort of routine when we start those streams. It's always nice to see familiar faces and new faces as well. As a way to sort of kick off the conversation, and while you guys start, please say hi in the chat. We are literally just 2 days away from the new Zephyr release. Zephyr 4.2 is just around the corner. Video is going to be a big theme, certainly, and we're going to talk more about that. But just one thing that I wanted to sort of put on screen real quick. So see again, this is documentation for Zephyr release candidate 3 towards 4.2 release. One thing that you may not, frankly, we should put it someplace else so that people are aware. But there is a thing that we've started to document. I don't know. I think it's been a year or so since it's there, kind of buried in the documentation. Again, I think we should improve that. But yeah, the way Zephyr works is that you have West that helps you set up and provision your workspace with your Zephyr sources and all the HALs, modules, libraries, and whatnot that you need to do your thing. And it turns out that not everything comes with and from the Zephyr open source project. You might be consuming stuff from third-party sources, and that stuff, it's probably like open source projects on GitHub and whatnot. If those projects have the right metadata in them, you can really easily pull them into your workspace. Things like connectivity for building USB to CAN firmwares and EMLearn for machine learning at the edge, or things like libmpix, which is today's topic. Kind of a long segue, a long intro, but it was sort of an excuse to get you all make you aware of this area. If you are maintaining an open source project that happens to be a nice addition to Zephyr and works well with Zephyr, you might want to get added there. Just send a PR. We would be happy to list it, have like basic instructions on how to provision it and stuff. And again, libmpix is actually what we're going to talk about today. Video in Zephyr and video in Zephyr together with libmpix for advanced image processing. So with that, let's actually bring our guest. I don't think I've ever done that long of an intro, but Joshua, welcome. Thanks for joining us and taking some time during the summer to update us, tell us all about video image processing. So you've been very active in the project over the last few months. You're effectively a co-maintainer of the video subsystem. Do you want to tell us a bit more about yourself?
Yes, I'm Josuah. I work at Demangeon, which is a design service company making Embedded devices based on FPGA and also involving microcontrollers inside the FPGA or separate. And I am in France, working from remote, and in Brittany. And yes, I've been incrementally more curious about Zephyr RTOS and consider contributing as part of Vision. And then realized that it will need some maintenance. So joined the existing team of video starting from long time ago, and with incrementally more stakes and maintainers getting involved as well as vendors pushing their drivers for their own hardware. So it's been very great to be able to see all that evolving in and around the video area.
Nice.
In addition to that, there's also big thanks to everyone who's been involved in the video area, but also surrounding area who are necessary because video never stays a single purpose thing. It goes out through protocols and all sorts of things. So Zephyr is a very good ecosystem for that, I believe.
Yeah, and those those external modules that I was mentioning, it's really nice to see more and more people and existing projects that have been around for quite a while that end up going sort of the extra mile and adding the the YAML file that helps people consume their projects even more easily and pull third-party projects into the Zephyr ecosystem. So yeah, that's really, really nice. So yeah, tell me about libmpix. Like it's pretty new, right? I think, is it something that initially you sort of thought of maybe contributing to Zephyr upstream, but then sort of realized it's actually, it doesn't have like strong dependencies to Zephyr, so it just happens to be a generic image processing library, right?
Absolutely. And there's even a version a little bit before Zephyr that was for a particular product. And then we thought this does not need to be a part of a product. It's useful to do different things on just this one product. So then we thought about contributing it to Zephyr, but it will have been burdening the maintainers to have yet another very application-specific data processing that has nothing to do with drivers and system programming. So much easier to make it on top of Zephyr rather than under Zephyr. Absolutely.
Yeah, it's just like, basic processing. It's not like you require, basic for the lack of a better word, but it's not like you require device drivers or like anything Zephyr specific. It's just computing algorithms and stuff. Yeah.
Absolutely.
So I'm going to put your screen on. So yeah, you have, and I dropped the link. Is this libmpix.org, right?
Yes.
Yeah. Okay. I'll put the link in the banner. So yeah, tell us more. Like, how does it work? And I think you have some maybe some demos to sort of drive the conversation.
All right. Library to process image data is a challenge. You have a lot of them on Linux, for instance. And it is tempting to be porting OpenCV and just use OpenCV on microcontrollers. And some people have been doing that. Here, it is a slightly different approach. And the status quo is that microcontrollers that were not built for image processing have very few memory available. And if you work at a classical small resolution, for instance, VGA, if we use raw image sensor inputs, the smallest form of raw data that can be used is 1 byte per pixel. And if we want to process the data in RGB, we need another output buffer for RGB. And that's already 1 megabyte of RAM, which is not every microcontroller that is capable of processing the video feed with the CPU is able to handle so much data. And we ended up with
plus you might actually need also almost like the same amount of memory to actually display the images. Like if you want to...
Yes, a frame buffer. Display frame buffer also will require that. And if you want to use ping pong buffers, you use even more buffers. So that's not a good amount of memory to require. And one possibility is to process the data line by line and try to fit all the algorithms so that they can fit in just one line of conversion at a time. And if the goal is to ultimately compress the image as JPEG, the output buffer is very small, the input buffer is very small, and the intermediate buffers is what we want to eliminate. So one way to do that is to process all the data line by line. but not every processing step can be processed in just one line. Sometimes you need 2 lines. For instance, debayer converting from RAW to RGB, or JPEG needs 8 lines of input. So you end up with some kind of schedule. So you need to fit 8 lines into blocks of 2 lines into one block of 8 lines. And you need to manually organize that.
Actually, Joshua, I think you might be sharing something that we are not seeing. I think we
Okay.
see the libmpix website,
Okay.
and based on how you're moving your mouse, you're probably showing something else. Yeah, that's okay. We're good. I think you can hide that pop-up if it bothers you.
Right.
You can click on the link. But yeah, okay. I think we're
Thank
back.
you. All right, thank you. So I was showing that there was all sort of scheduling of line of data to put into processing blocks that have different number of lines they can process. So it's quickly started to become a bit complex to handle the different number of lines. You want to do line by line processing, but how many lines at time do you need for every block? If you want to invert 2 blocks, you will need to reorganize all the scheduling you did. So it becomes too complex. Easiest is to place some kind of data structure, like a ring buffer, in between each operation. So you do not have to worry about in which order the lines are processed. You can invert 2 operations anytime you want. There are still ring buffers connecting the things, and the libmpix will adapt the space of every operation. 2 lines at a time, 8 lines at a time, 1 line at a time. And you can forget a little bit. This permits to bring a high-level abstraction on top of image processing, and this is an example to process data coming from a webcam, from a camera, and export it. It process data from an image sensor on a microcontroller and export it as a webcam using the recent UVC support. So we have a relatively small script that have relatively few dependencies, just one library to install, and that's about it. And to add in west.yml, and you have a relatively lightweight API as well, where you load an image from a buffer, for instance, video buffer. You specify the format, and you have now an image structure you can process. Here, for instance, we convert it to RGB. We can insert custom image processing in RGB, for instance, but now we do not have the actual full RGB buffer. The RGB is virtual in a way. It will be processed line by line. And then we can convert it back to the original format after processing it and going back to a video buffer so that it can be sent over, for instance, USB or do whatever you want.
So how about, like, I'm assuming that some algorithms or some like processing requires more context than just one line to do stuff. Like if you want to do, I don't know, like blurring or enhancing, so it automatically figures out how much lines it sort of needs to buffer to do its stuff based on like what you have in your pipeline. It figures out how many lines to keep track of. Is that how it works?
Yes, exactly. These sizes are defined within each element. The element says, I need this much line of context, and
Right.
the buffers will be planned in consequence. So you do not have to manage buffering. This is out of the way. For instance, if you specify I want low quality but fast debayer, which is raw to RGB conversion, you have 2x2 buffers, or you have 3x3 grid to process. So you need 2 lines of context or 3 lines of context, and depending on what you select, you have the
and usually I guess like 3 lines is as much as you like. It doesn't go 5. Okay, but yeah, that's at least that's much better than 240 or however many. Yeah. Okay. Nice.
So let's see this code example that we had on GitHub earlier. We get an image struct, we load it with a buffer, we convert it in RGB, we convert it back to the original format. For USB is usually YUYV, and we put it back into the buffer struct so that we can continue with Zephyr types. And if we just load that, we have a NiklaVision MCU connected, and now it's loading it into it. So let's look at the output. We will have, I need to restart them. So let's look at them one by one, by the way. Pouring on everything. So we have a few examples. So this is a NiClaVision output. It shows a relatively small image, but with good colors, and we show that the RGB data comes in, comes out, no modification. The image looks fairly normal. Side by side, we have, so this is the older version of libmpix, and this one uses a Raspberry Pi image sensor, Raspberry Pi V2, with an adapter module from CEST Studio, which is a Grove module, with a HiMax chip that converts the CSI to JPEG. And this is for this chip that we originally developed libmpix, so that it can handle larger resolution because we have a very large image sensor. So to be able to process all of that, we needed to store the full, biggest possible image in RAM, but then there's no more memory to process it. And for curiosity only, we have the Tiny Clunks, which is a platform that we developed at Univision, which is a much higher resolution, the same sensor, Raspberry Pi camera, but without any processing. And this is what an image sensor looks like when there is no extra processing associated with it. For instance, if we turn down the light, the image becomes darker without being compensated, but the other image sensors compensated the light, and we can see that this gets brighter, and if we increase the light, they compensate back, and they get always the same brightness. So the role of processing the data and also controlling the sensor is included inside of the image sensor in the case of Arduino NiClaVision, which is the bottom right here. It is present in with the ancestor.
You can disable it, I guess, like if you want to take control, or is it always going to be semi-automatic?
It is possible to disable it, and it is going to be useful. We will see very soon why. Not enabled in the driver, so I cannot demo it now. But if I have a patch to disable the automatic exposure, for instance, to experiment. One advantage of disabling the auto exposure and all the processing from the image sensor is that the NiClaVision has excellent image quality, but as soon as we start reducing the light, and I will reduce further, the image really starts to show some strong noise. And it is not the same kind of noise that has small dots like salt and pepper noise. It's horizontal lines, and this horizontal line noise is coming from all the digital processing that is directly inside the image sensors that corrupts the sensitive analog process of the image sensor itself. So the process of grabbing photons and turning it into electric signals is being polluted by the low noise, by the digital processing inside the sensor itself. So to avoid that, there is no other choice than disabling the processing from the sensor and using the processing on the chip. And for instance, the Raspberry Pi camera has other defects. For instance, color tuning is not excellent. We have to adjust that a little bit, but it has absolutely no noise. And the Raspberry Pi 2 camera, the IMX219, has image processing done outside of the chip, so that does not pollute the sensor. So to get
and
better,
by the way, you kill your main webcam, the one pointing at you. It's effectively black now, so I don't know.
Yes, because I turned on the lights, so I'm not. We don't see anything right now. I'm gonna turn back the light on.
Also, yeah. Oh, wow, that was okay. I thought it was another kind of black. Okay, you're back.
Right. It's just black in this sense.
Okay, awesome.
How about some?
So we have a question. I think we can feel free to just keep it at the back of your head if the timing is not right. But I meant to ask earlier, and Roman is asking basically about like hardware acceleration, specifically for JPEG compression. Is there a way to offload on a dedicated hardware unit like STM32N6? And if not, like how do you typically handle the ability to potentially override or specify custom hooks for specific like processing?
I will go more in depth later, but to give a high-level overview, is that libmpix offer adapters between the libmpix API and very basic functions. And the very basic functions are there so that it's easy to implement hardware.
Did we just lose you, Joshua? Or is it me? All right, we lost Joshua for a moment.
Hardware acceleration backend.
Okay, you were offline for a moment.
Okay.
Can you briefly restate what you just said?
Absolutely. In libmpix, there are planned already wake functions that are meant to be overloaded by a particular implementation that provides a particular accelerated version of every function.
Right, yeah, makes sense. Okay.
This is going to be used for SIMD support coming.
Okay. And yeah, I think your internet connectivity might be flaky. I'm double checking whether hopefully it's just me. Yeah, okay, so people confirm that, yeah, you seem to be cutting off, Joshua.
I think I went offline.
Yes, you did, and you're mostly back. At least audio is back.
I do not hear you right now, so maybe we went offline.
I can hear you, and
Okay,
we can hear you.
Okay, so that was just okay, no problem.
But yeah, your different video streams are crashed right now.
Okay, you sharing.
Let's see.
Right.
Okay, you're back.
Okay. Okay.
Yeah.
Sorry about that.
No worries.
Okay. Do I have 5 minutes left?
No, you have 35 minutes left.
Ah, perfect. So we can play a little bit.
Yeah. I would have been freaking out by now otherwise. Yeah, you might need to unshare, reshare your screen. That doesn't seem to want to come back. Can you try that?
Any better?
Yep, you're back. Oh,
okay.
Whoa, yeah. I saw Clippy for a moment. That was fun. Did I see just Clippy like in ASCII heart in your code editor for a moment? Yeah, I didn't
Yes,
that.
That's a Cocoon editor with a Clippy inside.
Okay. All right. So this is the step where we sort of fill in the blanks and we put some fun image processing in place where you have the comment right now.
Exactly. We now insert custom image processing here, indeed. So the main library of mpix to convert data is mpix image. That's a user API. And for instance, we can do some kernel processing. So it's not kernel in the sense of computer kernel, but it's kernel in the sense of convolution kernel. The same kind of operation, you have a neural network convolution, but instead of doing a whole neural network out of convolution operation, it's just one convolution operation and the output is stored in the output image and stops there. It is a kind of operation you use for denoising, for performing blur as the opposite, and sharpen filters, and all sorts of filters like that use pixels spatially, rather than just converting the brightness of one pixel. So let's see if we can use a classical example of kernel processing, which is edge detection. So we always refer the image, and then we have a choice of kernel. You can find that in all the documentation. And I think the size is, well, I have to check the documentation. That's a good example to see where do we find documentation also. Kernel processing, and we want to have edge detect. Should bring us to edge detect. And it's 3 by 3. So we have a 3 by 3 operation, specify 3. And let's go again. We just perform edge detection, and that's it. The edge detect.
Oh, you have a typo in there.
Right, grammar.
That was easy.
Yes.
So, folks, so thanks, Romain, for the question earlier. And of course, please line up all the questions you might have for Joshua in the chat so that we can take them. Okay, is it?
It's coming.
Oh, this is when we lose you again. This is going to be interesting. Time for questions, people. Please, please line up your questions. And
so in comparison with other images, you have the.
So Joshua, you're breaking up quite badly. We lost you again
sorry.
for 20 seconds. It seems to be mostly back.
All right.
I don't know if there's anything you can do to fix it. I guess not.
Is it any better now?
Your video is not back. Your at least
right.
The screen share is fine. But you're back. You're back.
Okay,
but yeah, if you can do anything about your internet connection, which I doubt you can, that would be great.
That would be great. Maybe I will just because I'm mostly doing demo now, so I can cut the camera.
Sure. Okay. And I'll go off screen as well. Joshua, I think you, whatever you did, you removed your mic and camera, so we can't hear you anymore. Yeah, unmute yours. Yeah, should be better. Let's see. 1, 2. 1, 2, sound check.
You can hear me and
yes, you're back. Sorry, folks. Sorry about that. Yeah, we are mostly back, I hope.
All right. So basic of edge
detection. It's a video tech talk, so it's fine. Like we only need the video, right? Only need the video stream. No voiceover.
Even better.
A question from Umesh. I was actually just going to ask whether there's a way to know how much overhead whichever kernel is adding to the processing pipeline, or another way to ask the question, I guess, is to like, can we see the frame rate and potentially the impact of the processing on the frame rate?
So for all the performance-related questions, there's going to be 2 ways to check it. One is to include and remove an operation and compare. It's as easy as commenting something out. Another way is to, there's inside libmpix, the built-in benchmarking. So the problem when you process data line by line is that you cannot measure start and stop, because you will be doing the first step on the first line, and then you will doing the next step on the first line, and you will process everything line by line. So you do not have the start of operation and stop of one operation. They are all interleaved. So built into libmpix, there is timestamping that accumulates the time spent on every operation and gives a breakdown at the end already there. So it is storing the information inside to be able to tune the performance and work on that. For the memory overhead, it's possible to, from a pen and paper, you have this pixel format, this number of window size, number of context line, and you can make the multiplication, that's the actual buffer. And also, you can compare the amount of memory used before, after. And for the demo, I'm using 16 kilobytes of RAM. For intermediate, the input buffer is still full size. Cannot, the hardware needs it, but the actual intermediate buffer are 16 kilobytes.
Nice.
By default, it's 4 kilobytes. So I had to increase a bit for larger kernels. Indeed, there's a little bit more operation. 5x5 required a bit more.
Yep, makes sense. Or that would be the case if you were to use, but you're already using RGB24, so it's not like you. Yeah, okay.
If you use grayscale, it's also a way to reduce the size of the intermediate buffer. Also, that's true.
Yep.
Right. Are there other questions?
Well, I guess, I mean, we can point people to the documentation for that one, but what kind of image processing is available right now? Like, can you sort of like at a really high level, like what kind of operations are available?
Absolutely. That's the supported operation pages, support documentation, supported operation.
Right.
And we can have we can try a few because we are the ability to just insert some line. And for every operation, you have a pixel format conversion. You have a Bayer, so debayer has a separate API. Convert to palletized formats. QI format is a compressed format which is lossless, lightweight, so it can be done with software only. Some image correction for gamma correction, black level, and white balance, classical operation of image enhancement. Kernel processing, so no modification, edge detection that we saw. And let's try a denoise afterward to see if we can correct the horizontal line noise we saw.
So wait for the gamma thingy. If I were to be interested in doing some kind of auto exposure, I do need to know about all the lines, right? To know what's the blackest and what's the whitest. You know what I mean? Like how would that work?
How would that work? Is so there is a demo ISP to show how to build a complete auto exposure with libmpix, and there's auto exposure in it, and all the control the exposure, the black level, and white balance. It will do that from statistics. And how are the stats collected? There's also documentation on that. The statistic will sample pixel from the image and compute statistic on that. How the pixel sampling is done. So supported operation. At the bottom we have statistics. Value sampling. How do we sample the pixels? There is a library for now. It's only doing random and for RGB format output, but it can sample any kind of format. So for instance, you have a big Bayer image format, raw image format. You cannot sample pixel in RGB directly. But libmpix is an image processing library toolkit. It got all sorts of software that makes it easy to do debayer. So it will pick random pixels and perform the libmpix operation on the random pixels only. So we'll pick 1000 pixels, which is relatively small, and then it will do debayer only of these 1000 of pixels, and it will compute the statistics on these random sample pixels. And that's where you can have RGB value directly out of a raw buffer that is not RGB. And that way you can you don't have to convert the whole image to get the statistics, and you have these formats supported for the statistics.
And by the way, can we get you to write Zephyr documentation? Because, like, I mean, the documentation for libmpix looks awesome. I'm sure we could. I mean, yeah, that was it. But yeah, no, that's really, really nice to see such a comprehensive documentation for.
I promise. For video areas, there's a lot of documentation needed. So the API are almost all stable. We will get to it also. How to implement the internals.
Okay, so yeah, I think I interrupted you as the sort of like gamma and white balance operations, resizing. Okay, blur. Okay.
For now, there's only low quality subsampling. There's going to be more variants of each operation because there's a lot of trade-off you can take between speed and performance. Some interesting artifacts. We remember that there was some noise when we reduced the light. It did not seem that critical, but if we do that on edge detection, for instance, we reduce the amount of light. The image is still black. It was black before. But then edge detection, for instance, gets really difficult to see the details because of all the artifacts of the image. So in some case, for instance, if you have good light and the Nikola Vision does have an LED that permits to bring control lighting to the image to always have good lighting condition, even in plain dark. But if you need to work with low light and then do extra processing on top, it becomes nice to be able to have some good image as a source. But let's try to see if we can simply correct apply the noise to try to avoid the noise. very strong denoise. Reloading into the nuclear vision. All right. We restart the feed. We started. There we go. And now we have very strong denoise. And yes, indeed, we do not have any more noise. And we sort of still have sharp edges. The edges are very sharp, but the details are gone. We do not see any details back because they were too close to the noise level. The noise was mixing with the details we were trying to get. So we are doing too strong denoising. But still, maybe that's what we want to do. Maybe we want to only see the big outlines and not the small detail. So now let's try to combine. If I have enough memory declared, let's see. And now we can. It's very frequent for image processing to combine multiple successive operations.
Yeah.
First, you do blurring, and then you do edge detection.
Yeah, like in a normal situation, one would consider blurry image to be not what you want. But if you combine with edge detection, it's actually, it helps extract what you really care about.
That's true. It acts as a filter that modifies the output. And if you want to catch something a little bit particular in the image, exactly, that's So we have a different edge detection and different edges. If we wanted to get rid of the small details, now we have them out. We still have the strong edges all around. Maybe you wanted to recognize the digits that are now a little bit more out of details around the digits or something like that. So that's not OpenCV yet, of course, but a little bit of...
I was going to say, like, it feels better, quite frankly, like being able to to do this with just literally 2 lines and yeah. So there's a question from Julio in the chat. I mean, so I don't know, I think you might have told me in the past, but if I remember correctly, you are reasonably new to video, so I'm sure you did lots of reading, lots of learning. So Julio is asking, is there, like, what are some useful resources such as a book to learn more deeply about the topic? And of course, like as we can see, like right on the screen, this is probably something that can be really useful for TinyML. Like when you get to the point where you extract like really meaningful info from the image, just one extra tiny bit of machine learning, and you can probably do wonders. But yeah, are there any useful resources you could point people to? And we can also take that offline and share the links in the comments afterwards. But anything that comes to mind?
Absolutely. I will say ecosystem and communities will contain useful resources. For instance, for building ISP, image signal processor, it is libcamera that will have the software that removes the taboo, the commercial taboo about image signal processing, because that regenerates a lot of good contracts that people do not want to let the information of how to build good ISP out to some extent. So libcamera does an excellent job at democratizing and providing simple implementation, which libmpix also uses for some elements, very simple things. But if you want to quickly reference ISP, you can look at the libcamera.
Okay. And I guess OpenCV is not too bad.
OpenCV has an academy and a very good learning material as well, excellent documentation of how to do anything. Some libmpix operation, for instance, dewarping, it's not supported yet, but it is in the work to correct the fisheye effect of lenses. And for that, you need to calibrate your lens first. And there is an OpenCV script to calibrate the lens. And then the calibration data is used in the microcontroller. So OpenCV is a gold standard for doing anything with image processing on desktop, for instance.
And I guess maybe you've checked, and like, is there a reason why they didn't use a similar approach as you to? I mean, basically, what prevents OpenCV from running on MCU? It feels like it could.
It actually does run on MCU. Someone did port OpenCV for doing edge detection, for instance, as a classical example that's always used. It does work on machines with more RAM, and then you have fewer RAM for the rest of the application. And also, if you use, for instance, there's a project called OpenMV, Open Microcontroller Vision, maybe. And it's an excellent project which uses Python as a base language for everything. And it works very well. So if you want something very complete, you can use OpenMV, and it only works on full frames. It works on more recent chips. It works better on more recent chips with more memory that permits to process larger image. With vector acceleration, they have all the vector acceleration ready, and it actually works. There's no downside to it at a high level. But if you use a microcontroller that has a little bit fewer memory, or if you do not want to use the MicroPython environment, OpenMV is closely related to MicroPython, then you will probably need some kind of alternative. And because we needed that alternative, we started to provide it. It's probably more fit as a small intermediate preprocessing element to get a good image and to get preprocessed image with transformation of this kind, rather than the final thing that will do all the custom processing on top of the preprocessed image, at least as a first step. But yeah, all these other projects are actually great, and they also provide lots of great things. So do check them out as well.
Cool, thanks. All right, so what's next? Do you have like other interesting?
Yes.
Okay, interesting processing algorithms. There was a question earlier from Romain again. Is there an option for static/slab allocation planned?
So for now, it's using a K-heap, and I don't have a plan to do something else just because I did not have the occasion to use something else. But it's not difficult to change that. And if that became a use case, that's just K-heap defined there.
Mm-hmm.
And providing different allocator is just a matter of maybe K-config to select a different allocator. And well, I mean, that basic wrapper, that's all there is, right? These 3 lines. Define the heap and use it. So like SMH, shared memory heap, allows to use external SDRAM. And that's an interesting point. When you use SMH, you probably are interested in external RAM. And libmpix allows to use the full input buffer from SRAM, but then do all the intermediate processing from the internal RAM and maybe even TCM. So the very, very fast, very one cycle, no low latency memory. And this means that by reducing the size of the intermediate buffers, that means you do not need to go back and forth with SRAM. You have all the intermediate processing that fits in internal RAM or TCM, or maybe sometimes CPU cache, depending on the size of your memory. So that's also a good way to process things. Likely, the internal CPU memory will be useful to most useful for internal buffers.
Yep. Okay. And you might let's take some risks here, but if you want, I think you can try and come back on camera. It looks like your internet is back. Maybe this is asking for trouble, but
let's try.
There you go. Cool. It's actually not working though, so that's weird. Let's see.
Wait.
Yeah. I think it's good. So please bring back your screen, and it should be good. I knew this was asking for trouble. Yeah, just share your desktop again. Let's see. We have a question from Luis. Yeah, it might be good to have an option for the app to own the heap so that multiple processing pipelines don't collide with each other.
Multiple processing pipeline won't. Okay, so you want to have different memory pool for different application. That's a good use case. That's an API to add. It's not currently supported. However, it's something that should not be difficult to add. There's probably some way to specify the allocator do some processing, and specify a different allocator, and do some processing, something like that. Yes.
Yeah, makes sense. Okay, but yeah, great questions, folks. Please keep them coming. Okay, so what were you gonna show us next?
Right. Maybe it's an interesting point to start looking a little bit of how to, so now we have a hang of how to process the data. Maybe it's good to look at how to implement new operations, how to contribute more elements into libmpix. So there's documentation for that as well. That's a good starting point, and we can go into the new conversion function. So it looks like a big pipe machine. There was an effort to try to bring something relatively easy for the developer. And for every kind of operation, we'll have different function signature of different API needed, because sometimes you will need one pointer to just one line. Sometimes you will need several pointers. Every type of operation defines its own local abstraction to have something very basic. For instance, here you have a source buffer to convert a line between big endian and little endian. You just swap the bytes. As a basic example, you have source buffer, destination buffer, and the width. That's the most typical basic API you could have. And then a loop that runs for every line. It shifts the pointer. You can also work on index if you prefer. And then you just swap the bytes with some bug on the tab. But then you just swap the bytes, and then it registers an operation, which is how you will tell the libmpix engine that now there is a new operation available. It uses this function, it has this internal name, and it works for converting from this format to this format. And that permits, for instance, to define a new format without supported. It's not supported in libmpix. You can just add the new format very easily without having to investigate the entire internal library. That permits to go, and then you will be able to find your format through the public API. It will be registered in a table of conversion operation. You call the convert operation on a buffer that is this format, and you will have this destination format. It will match with a function that you had to convert from RGB little endian and big endian, for instance. That gives you some, and you can register the same function, because swapping endianness is common in the same function for the other direction. And you use a lot of formats, same function, so you can register the same function multiple times also. If you want to implement hardware accelerated version, that will be the same API, except you do not have to register the function, etc. That is already known. Instead, you implement the function by clashing with a name that is inside libmpix, and every libmpix function are defined as wake alias, so you can override the implementation with something that works better for your platform. That way, when vector extensions for Extensa, for instance, ESP32, S3, S2, or for RISC-V that have a vector extension coming, and for all the Cortex M55 with vector extension, or M33 with DSP extension, then you will probably want to overload the implementation in libmpix for a hardware accelerated version, as that's available on the platform.
Okay. Yeah, so that's conversion, and then I guess the other one was like actual transformation, I guess you call it, or?
Right. Transformation, let's go to libmpix repository to see an example of operation. Operation image correction, for instance. For image correction, you do not want to specify the input format and output format, because it's always the same. You correct an image, the output data doesn't change.
Mm-hmm.
You want to specify the type of operation. So here, for instance, you want to adjust the black level, that is the darkest color of the image, that just apply an offset to the image data. Well, you will have the same implementation, because it's just a subtraction, the same implementation for everything, and you register that as black level correction. So you do not have to specify the input format, etc., every time. These are these macros that take care of all the internal work of registering the operation. So you have a relatively compact operation definition every time. And for every time kind of function, it's always kind of compact for color correction, different formats. So that you can implement a new operation not supported by libmpix without having to look at the internals. If you want to look at the internals, there's also to define a new type of operation. Maybe you want to try JPEG compression before it's available. So you can also, new type of operation, you will have to deal with the actual macro. You have to define your own macro that does your custom operation, and that will register your custom operation as part of libmpix, and then you will define any format that is specific to your particular operation. Then you can define your own helper, so that you do not have to specify all the parameters every time.
And so back to the tiny ML topic, like, would you see someone hooking up their neural network processing right into this pipeline, or rather sit before or after it? I guess it's possible, right? To just, that's
Yes.
an operation that taps into TensorFlow Lite or whatever, could be.
And the output buffer will be the detection result, for instance. So it's possible to wrap any kind of ML network. There could be two advantages to that. One is to reduce the API work. So it's not that libmpix gets AI features, but rather that libmpix brings some glue to reduce the amount of manual work with integrating two things. So that's where you can define new operations that will need very large input buffer, because you want the full buffer to pass to the NPU. But if you have some NPU kind of operation, for instance, we have convolution, you can also process the image in a streaming fashion, and then it starts to become very close to the internal architecture between libmpix and TensorFlow Lite Macro, or now Lite RT, or also a lot of other software-based neural network framework, which work exactly the same. So you can glue so that you don't have the large intermediate buffers also. It's an API that's possible to build, bridge. That's a good point.
Yeah. And by the way, that's the first time I hear about Lite RT. I didn't realize
a new name for
like a revamp or like a VNext for TensorFlow Lite. Okay.
Yeah. They like changing name as
we have a question from Alain asking, should there be some kind of helpers within the video subsystem to allow interfacing libmpix weak functions with the video subsystem APIs?
That would be a great way. Looking into the actual way operation are implemented, for instance, operation JPEG, which is a placeholder for now. We can see how JPEG data is being JPEG encode, how data is being consumed as part of a MPix operation. Where is it? There we go. So we will focus on this very small fragment at the top. In a libmpix operation, instead of having a pointer to a buffer, you get an input stream, and you will request line from the stream. You will request input line, and you will request output line. So here you load the buffer with line one by one, and you store multiple pointers, and you push line of output. Here you get a full output buffer. So that means that you can request, I want 5 lines, I want 10 lines, I want 30 lines. The operation decides itself how many lines it wants. And then you have the output buffer to push the data out. So one way to say is, instead of requiring Zephyr, a particular method to process data in Zephyr, the goal is that libmpix adapts to Zephyr APIs. And for instance, there can be an adapter in libmpix that, instead of processing data directly, it will load the input data into a buffer, submit the buffer to one device, and get the output data out of the device, and then that will be continuing the processing, so that you interleave hardware in the middle of a libmpix flow. That way you do not have to write wrappers around video API, but you have to write wrapper inside libmpix to include video device are part of it. That way, it's also very easy to adapt it to other kind of APIs and accelerators that are not only exclusively video. For instance, LVGL, if you want to have a LVGL and do post-processing so that you adapt the output of LVGL so that it looks good on the display. You have color processing, and you can also try to do things like that. So it's not too specific to one area either. So that would be a very good point.
Okay, nice. Thanks. Just FYI, we're just a couple minutes away from the top of the hour. Was there anything else you wanted to make sure that we really get a chance to see?
Yes. Let's look at how the debayer is tested. No, that's So this is a unit test of libmpix, and it is a pure CMake. It runs on POSIX system, so it uses libc, printf, etc. And to be able to get an output, it printed on the screen. So this is image processing happening, but instead of this is the input image, and we see there's a little bug here, something that's maybe it's a bug in the printing function, maybe it's a bug in the unit test. We have to check, and we see the outputs of the processing here. So we bring colors directly in the terminal, which is kind of convenient so that you do not have
to actually
display.
Write tests, but even check the expected output. Yeah, exactly.
Otherwise, you just have numbers, expected input, expected output. This number is wrong. Just show me the data. That's expectation. Yeah. So that's one way to write new operation with libmpix is to start from a test, unit test, very basic test flow. And implement the operation needed and show the output on the display and what that works integrated into.
And you can even capture that output, embed it in the documentation almost, as to show the typical.
Yes, I think there's some script to turn that into HTML for an escape code, for instance. So you can show the result. So we need to put better CI because Zephyr has good CI, but this is not Zephyr specific. So we need to rebuild all of the awesome Zephyr CI into a watered down version. Maybe we use the Zephyr port to test libmpix. That's a better option, maybe.
Yeah, well, definitely Twister is brings interesting glue for all things testing. Yeah, for sure. Yeah, we're sort of running out of time, I think. And I'm sure people will agree. We could probably talk about all this for many more hours. People in the chat actually tell us, I think, quite frankly, I personally think it was one of the best topic and episodes we ever made. So maybe we need to do a take two to do an even deeper dive. I know there was a question from George we didn't get to. So don't necessarily try to answer it, Joshua. But it's someone was asking about doing a deeper dive into the video source setup and stuff like that. So maybe we maybe we do another tech talk in the future. Folks, please make sure to subscribe to the LinkedIn page, the YouTube channel, so that you don't miss future episodes. Tell us in the comments if you have questions. Even if you're only watching the recording, we will make sure they get answered. And we will be back in a few weeks. Any final words, Joshua? Anything else? libmpix.org again, I guess, is where you want people to go, come and contribute.
Best, yes, but worst network.
Yeah, that was pretty bad. But, and actually, you're right. That I don't think that ever happened. But yeah, it was only a few minutes, and I think people, people didn't drop. So that was good.
More to come
again. Yes, thanks everyone for watching, and thanks very much, Joshua, for being on the show. Bye.
My pleasure.